Hello dear friends, welcome to a lecture on Euclidean ring. In this lecture we shall study necessary and sufficient condition for a maximal ideal in a Euclidean ring. I have written here as a theorem which states the necessary and sufficient condition for maximal ideal of Euclidean ring. The theorem states that the ideal A generated by A naught is a maximal ideal of the Euclidean ring R if and only if A naught is prime element of R. Or the same statement can be written in other words as, or the ideal A of the Euclidean ring R is maximal if and only if it is generated by some prime element of R. Here we have written A naught as a prime element. So before considering this proof of the theorem, we shall just revise what is ideal and what is maximal ideal. We have studied these in our earlier lectures. You may refer these lectures which are in the playlist of ring theory. So ideal, U is ideal of a ring R if it has two conditions. U is subgroup of R under addition, and second condition is for every U belongs to U and R belongs to R, the product UR and RU both are in U. That is the condition for, or actually definition for ideal U. And when ideal is said to be maximal, this is the definition of maximal ideal. M is maximal ideal of a ring R. If there is another ideal U, ideal of R, such that M is subset of U is subset of R, then this U must be either equal to R or U is equal to M. So that means there is actually no ideal in between M and R. If we consider it as U, then this U is equal to M or this U is equal to R, then M is said to be maximal ideal. That we have studied earlier. And we have taken there an example of a Euclidean ring as a ring of integers, and if we consider ring of integers as z or I we have written with addition and multiplication, then an ideal generated by 2, this is an ideal generated by 2 which will be all multiples of 2, and that means 0, plus minus 2, plus minus 4, etc., plus minus 6 and so on. So actually 2 is a prime element, and therefore this ideal will be maximal ideal. So if A naught is prime element, then the ideal is maximal in Euclidean ring. This is ring of integers. But if you consider, so this is a maximal, or an ideal generated by 3 will also be maximal ideal. And here ideal generated by A is equal to A naught, ideal generated by A naught. Every ideal in Euclidean ring is a principal ideal. That means it is generated by a single element, and that all elements of A are multiples of A naught. Or here A is generated by A naught means every element of A is of this type, A naught multiplied by some x, x belongs to R. This is the meaning, and therefore here also 2 means all multiples of 2 in the ring of integers, all multiples of 3 in the ring of integers, that is etc. So these are prime, and therefore these ideals will be maximal. And we have studied this example in our earlier lecture, and if I consider this ideal generated by 4, then all multiples of 4 we will have to consider, and so on. But this is not, 4 is not a prime number, and this not ideal is not maximal ideal, because we have, see, this ideal 4 is subset of the ideal 2, and this ideal 2 is subset of Z. So 2 is these two are different. This ideal generated by 4 is here, and the ideal generated by 2 has this set. Therefore, the condition is not satisfied. This condition u is equal to m or u is equal to r is not satisfied here, and therefore this ideal is not maximal. But these ideals which are generated by prime elements are maximal ideal. That is the meaning of the theorem. And one example also earlier we have studied in the lecture of maximal ideal. If the ideal u is generated by p, where p is prime, and that means all elements of this ideal will be of this type px. P is prime and x belongs to z, then this is maximal ideal. This we have seen earlier. So now we shall prove the theorem. But in place of the ring of integers, we are considering here, or we are studying here, Euclidean ring. And now the proof. There will be two parts. First, actually we shall assume that first we will prove this. If A naught, if A is a maximal ideal, then A naught is prime element of R. That we shall prove. But we will consider its logical equivalent statement, which is contrapositive. If A naught is not a prime, then A is not maximal ideal. So that will imply the first part. That is the first part we shall see. We shall prove that if A naught is not a prime element, then A, the ideal A generated by A naught, is not a maximal ideal. So this is the equivalent to the statement that if A naught is not prime, then A is not maximal. Means if A is maximal ideal, then A naught is prime. So see, P implies Q. This is equivalent. Negation of P implies negation of Q implies negation of P. Then this is a contrapositive statement in logic, and therefore this statement is equivalent to the statement that if A is maximal ideal, then A naught is prime. Now we have supposed that A naught is not a prime, and therefore A naught can be written as product of B into C. Suppose A naught is not prime. A naught is not a prime element. Then suppose A naught is equal to B into C. Definition of prime. Definition of prime is we can say P is prime. If we write P is equal to AB, then one of A or B must be unit. And here if it is not a prime, means neither of A nor B is prime. And we have written this as A naught is equal to B into C, where B, C are in R, and neither B nor C is a unit. By definition of prime, we are writing this. It is not a prime, therefore both of this B and C is not unit. That is the expression for A naught we have assumed. Let now B be an ideal generated by B, be ideal of R. Another ideal of R, and such that see, actually what we have to prove that A is not a maximal ideal, and we will consider A subset of B subset of R. When it is A is maximal, if A is equal to B or B is equal to R, then A will be maximal, and therefore we want to prove it is not a maximal ideal, and that means we have to claim that, or we have to prove that A is not equal to B and B is not equal to R. So we shall prove that, or we claim that A is not equal to B and B is not equal to R. Now if B is equal to R, we will consider this case first. What will happen? If B is equal to R, then 1 belongs to B, because R is Euclidean ring, 1 is in R and therefore 1 is in B. And now you see B is generated by this element B, therefore this implies 1 can be written as multiple of some multiple of B, that is xB, for some x belongs to R. So we can write 1 as xB, and if we can write 1 as xB, then by definition of unit, see, either x is a unit or B is a unit, then either x is a unit or see, 1 is equal to xB, then both will be unit, x and B are unit. But what is our supposition? B is not unit, neither B nor C is unit, B is not unit. So then here we must have like this, then x, B is a unit, x is a unit and B is a unit, because both are, what is definition of unit? The element which is multiplicative, which has multiplicative inverse is unit, and here x into B is 1 means x and B are multiplicative inverse of each other, and that means both are unit. So therefore x is a unit and B is a unit. So then but we will consider this as B. This implies B is a unit. Also x is a unit, but we will have B is a unit. That part we shall select, because we have here B and C are not unit. Then B is a unit, and this is a contradiction, or this is not true, or this is a contradiction. And why this contradiction has arrived? We have supposed B is equal to R, and then we get B is a unit, which is not true, or which is a contradiction. Thus therefore B is not equal to R. Now what happens if A is equal to B? If A is equal to B, now we have B is an element in B, and therefore that B element also belongs to A. Then B belongs to B equal to A, and therefore this B, but what is A? A is generated by A naught, and therefore this B will be some multiple of A naught. B is some multiple of A naught, and therefore we can write B is equal to x into A naught for some x belongs to R. And now what this further says, see we have here A naught. A naught is equal to B into C. Now A naught is equal to B into C, and but what is the B? B is x A naught, and therefore I shall write this as x A naught into C. And here cancellation law holds in Euclidean ring because it is integral domain, and therefore what this says, or this implies by cancellation law, we get A naught cancels from both sides. We get 1 is equal to xc, and this implies C is a unit. The same reason, 1 is equal to xb, B is a unit. Here C is a unit. This implies C is a unit, and this is also a contradiction because neither B nor C is a unit, which is a contradiction. And why this contradiction has arrived? Because we have supposed A is equal to B, and thus or therefore or thus we must have A is not equal to B, and thus that we have obtained this result, that thus A is contained in B, contained in R, and A is not equal to B, B is not equal to R, means A is not a maximal ideal. Therefore A is not a maximal ideal. If A naught is not a prime. And this proves the part, first part, that is, see, if A naught is not a prime, then we have proved A is not maximal ideal, means which is equivalent that A is maximal ideal, then A naught is a prime. That part we have proved. Now second part we shall consider. Conversely, suppose A naught is a prime element of R. Second part of the theorem, which is converse part. Converse part means we shall assume A naught is prime element of R and we shall prove A is a maximal ideal. Conversely, suppose A naught is a prime element of R, and what we have to prove, that A is maximal ideal, which is generated by A naught. And to prove A is maximal ideal, we shall use the definition. Let U be an ideal of R such that it is in between A and R, such that A, which is generated by A naught, is subset of U is subset of R. And to prove A is maximal ideal, what we have to prove? A is equal to U or U is equal to R. Then A will be maximal ideal, that we want to prove. Now since U is an ideal of Euclidean ring R, U is generated by some element. Every ideal of Euclidean ring is a principal ideal. That means it is generated by a single element. since U is ideal of Euclidean ring, let U is generated by some element U naught for some U naught belongs to U. So this is we shall assume, and now this A is generated by A naught and U is generated by U naught, that we will have, and A is element A naught is in A, therefore A naught is also in U. Now A naught belongs to A and A is a subset of U, which is generated by U naught, and therefore this means A naught is some multiple of U naught. Therefore A naught is equal to some multiple of U naught, and that we shall write x times U naught for some x, for some x belongs to R. So this result we shall get. It is in U, and U elements of U are all multiples of U naught. Therefore this A naught will also be a multiple of U naught, and that we have written as x U naught. What this shows, A naught is product of these two, but our supposition is A naught is a prime, and therefore when A naught is a prime, this one of this either x or U naught is a unit, then and only then A naught will be prime element, by definition of prime element. This implies either x or U naught is a unit in R or unit of R. Now you see, if you consider the first possibility as U naught is unit of first as U naught is unit of R. If U naught is unit of R, both we will consider the cases. X is unit and R U naught is unit. If U naught is a unit of R, then if U naught is a unit of R, then U is ideal generated by a unit, and if an ideal contains unit element, then the ideal is equal to the whole ring. Then U is equal to R. So this is an example that we have studied in our earlier lecture. Since if an ideal contains unit element, contains a unit, not unit element but only unit. If an ideal contains unit, then it is equal to the ring. This result we have studied as an example, and therefore we get U is equal to R. If U naught is unit, then U is equal to R. And what happens if X is unit further? If X is unit, X is a unit of R, then if it is unit, then it has multiplicative inverse. Then it has multiplicative inverse, then X inverse belongs to R. And now what we have is A naught is equal to X into U naught. We have A naught is equal to X into U naught, and from this we shall write the expression for U naught, and to get the expression for U naught we may multiply both sides by X inverse. So this implies X inverse into A naught is equal to this X gets cancelled, or that is x inverse into x is unit, and therefore we get u naught, or u naught is equal to x inverse into a naught. Now you see this x inverse is in R and a naught is an element in A, and A is ideal. A is ideal, therefore this element belongs to A. That is definition of ideal. A naught is in A, this x inverse is in R, but the product must belong to the ideal. This belongs to A, since A is an ideal. A is an ideal of R, and thus what we have obtained is u naught belongs to A. But what we have earlier supposed is this relation. This we have supposed. That means see, A is subset of U is subset of R. This we have written at the beginning. A is subset of U is subset of R, and this A naught is in A, and now what we have proved, U naught, this U naught is in U, and this U naught we have proved is in A. So U is generated by U naught, or actually this is the relation. U is generated by U naught, and then this is also subset of R. So U naught is in U and that U naught is in A, means this U is subset of A. Therefore U naught belongs to U implies U naught belongs to A, and therefore U is subset of A. But here A is subset of U. A is subset of U, and what this together implies, they are subset of each other, means they must be equal. Thus A is equal to U, and that means we have assumed this. A is subset of U is subset of R, then we get either U is equal to R, this U is equal to R, or A is equal to U, the second case, and therefore A subset of U subset of R implies either U is equal to R or A is equal to U, or U is equal to A. And what this proves? This proves that this A is maximal ideal. A is a maximal ideal. Ideal of R, and this is what we wanted to prove. Assuming A naught is prime element of R, we have proved A is maximal ideal of R, and this completes the proof. So we have proved the necessary and sufficient condition for a maximal ideal in a Euclidean ring. If it is generated by a prime element, then and only then it is maximal ideal. So I hope you can understand this lecture. Thank you for watching the lecture.